Lab 4, Oscillations. The purpose of this lab is to analyze and predict the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We will do this by creating a computational model using Newton's second law, Hooke's law, and the energy principle. The findings concluded that the energy principle was satisfied because the total change in energy was relatively constant throughout the oscillation. The energy principle states that change in energy is equal to work. Since there is no work being done on the system, the change in energy is equal to zero. Therefore, the components of the change in energy of the system, change in kinetic energy, change in potential energy due to the spring, and change in potential energy due to gravity all added together should be equal to zero. In placing the given video into Tracker, we can see that the object is moving in both the x and y direction. This analysis gives us our initial condition. The initial position is negative 3.577 in the x component and 14.307 in the y component. The mass is taken from that lecture video of 0.402 kilograms. The initial time is 0 seconds, and the period, which is also obtained from the lecture video, is 1.524 seconds. Given this, we can find the spring constant by using the rearranged formula K equals 4 pi squared times m over t, which gives us the spring constant of 6.83 newtons per meters. We can then find L naught because we know that the magnitude of the force of gravity must equal the magnitude of the force of the spring, so L naught equals L minus mg over k, which equals 0.123 meters. Entering these initial conditions into our VPython code and inserting the name of our file of our actual obtained values from Tracker in order to compare them to the predicted times. We can now move on to the initialization of the section of the code. After putting in the initial conditions that we know, we then set L equal to the position of the ball minus the position of the spring, and L hat, the direction of the vector, equal to L over its magnitude. Then we can set S equal to the magnitude of L minus L naught. The next section of the code is where we calculate our energy values. Using our known equations of K equals 1/2 mv squared, UG equals mg delta y, and US equals 1/2 ks squared, ks times s squared. In the while loop of our code, we set the energies to what we found above, and then we edit the code below to say that the force of gravity is going to be negative mg in the y direction, the spring force is going to be ks times s times L hat, according to Hooke's law, and F net is the force of gravity plus the spring force. The ball's velocity will be the ball's initial velocity plus F net over mass times the change in time, and the ball's position will be the ball's initial position plus the ball's velocity times the change in time, and these are both according to Newton's second law. In this section of the Python code, we calculate our energy changes in each time step. We know that K is 1/2 mass times velocity squared, and then we solve for delta K as the change in kinetic energy, which is final minus initial. The potential energy due to gravity is the mass times G times the ball's position in the y component. The change in UG is going to be final minus initial, and then the potential energy due to the spring is 1/2 ks times s squared, and the change in US is also going to be final minus initial. When we run the module, we see that the blue line is the plot of delta K, the red line is the plot of delta UG, the green line is the plot of delta US, and the yellow line is the plot of all three added together, or the total energy. Because the total energy is relatively constant, we know that the energy principle is maintained, because we decided at the beginning of our lab that the change in energy was going to equal zero. Here is the comparison of the model data versus the actual data obtained in Tracker. You can see that the values are slightly off as it travels through the period. This could be due to energy that is dissipated and not calculated in our model. The top values are the x position and the bottom values are the y position. The estimation of the x oscillation period is 1.71 seconds and the y oscillation period is 1.64 seconds. Even though they are different, it does not really change the impact of the experiment because they are impacted by energy being dissipated at different rates during the motion, as well as the initial force that caused the object to oscillate as it did, which causes the slightly different periods. But, as discussed earlier, the model does relatively match the prediction that change in total energy would be equal to zero, so these periods have negligible effect on our model.